If you want to secure top marks on your Cambridge IGCSE physics practicals, you have to stop losing easy points on data handling. Today, we are cutting all the generic fluff. We are uncovering the exact hidden patterns examiners use to test Hooke's law, spring constants, and moments, so you can execute perfectly on exam day. Right, let's just get straight into this. Why do so many well-prepared, smart students lose easy marks the absolute second they face a raw data table? Honestly, it's painful to watch. Because a single data handling error, something as tiny as a missed decimal point, can completely snowball and cost you an entire grade boundary. You see, in practical papers, your physics knowledge just isn't enough on its own. Your data discipline is what's actually being tested. The stakes are incredibly high from the very first question. So the absolute crucial starting point is knowing exactly what these traps look like. If you look at the examiner reports, the same mark-dropping mistakes happen every single year, like clockwork. We're talking missing units in tables. We're talking rounding values way too early in a multi-step calculation, giving these vague explanations instead of actual scientific reasoning, messing up graph axis scales, and writing conclusions that just frankly aren't backed up by the numbers at all. And let's be real here, reading a textbook chapter on forces while you're half asleep on the sofa, that does not train your brain to spot a missing Newton's label in a high-pressure exam scenario. Now, what's genuinely interesting is how the actual syllabus structures these topics. Notice how the sections cover forces and turning effects, all the way down to stretching and compressing. Most students revise these as completely isolated, separate ideas. But the examiners, they don't test them that way. They connect them all under one massive testing pattern: practical data analysis. Seeing how these topics link together as one combined practical skill, that is your very first major quick win today. To beat this pattern, you need a bulletproof system. Enter the 4-step hidden pattern. It's like a cheat code, but it's just pure strategy. Step 1, state the core concept, like Hooke's law. Step 2, extract the exact evidence or data directly from the source provided. Step 3, apply your scientific reasoning to link that specific data to the concept. And Step 4, polish it off with precise examiner wording. This structured step-by-step approach is exactly what top band students use to lock in those critical method marks every single time. Now, in a moment, I'm going to show you the exact examiner clue about graph anomalies that changes a typical answer completely. It's a trap most people fall right into. But first, you really need to see this 4-step framework in action. Otherwise, that clue just won't make any sense. Okay, let's test your eyes right now with a little challenge. Pause and predict. In this mock Hooke's law data table for load versus extension, can you spot the fatal table design errors before we move forward? Look really closely at the digits in the columns and the text in the headers. Spot anything weird? Boom, there it is. This brilliantly illustrates exactly what examiners are hunting for: inconsistent significant figures and missing units. Think about it. If your extension column jumps from 2.0 to 4.55 without a consistent number of decimal places, you lose the mark. If your load header just says load without the / and capital N for newtons, you lose the mark. It's that brutal. These specific, tiny errors instantly destroy your accuracy marks before you've even plotted a single point on a graph. Let's see how this actually builds into your written analysis. A typical flawed answer might state something like, the spring stretches by 4, so the constant is 2. I mean, it's vague, it completely lacks units, and it shows zero working. Contrast that with a top band answer using our framework. Concept: Hooke's law applies. Data: a load of 8.0 newtons results in an extension of 4.0 millimeters. Reasoning: the spring constant, K, equals force over extension, so you take your 8.0 newtons, divide it by 4.0 millimeters, and you get 2.0 newtons per millimeter. That right there is how you lock in maximum marks without leaving anything to chance. You simply cannot cut corners here, because examiners operate by a very strict rule. The rule is, conclusions must be directly supported by the data and substituted values. I really want to let that sink in. Examiners will give you absolutely 0 marks for a perfectly correct physics concept if you fail to use the exact evidence and substituted values from the source page. You literally have to prove your answer using their numbers. All right, let's escalate this to a harder example involving moments and the center of gravity. Imagine an investigation where you are balancing a beam. Right in the middle of these trial runs, there is one clear anomalous result, a number that completely breaks the pattern of the turning effects. This right here is the exact anomaly trap I teased a minute ago. So, what do we actually do with this weird data point? How do we handle this anomaly safely to secure those critical method marks? If you just cross it out or, ignore it in your conclusion without explaining why, the examiner is absolutely going to penalize you. So I challenge you, what is the exact specific wording needed to fix this issue and improve the experiment's reliability on paper? Here is the examiner-style correction you must use to write perfect practical improvements, using the correct Cambridge terminology. First, explicitly identify the anomaly and state clearly that it must be excluded from the mean calculation. Second, check your experimental variables. For instance, ensuring the load was actually placed at the exact center of mass. Third, refine your graph scales to ensure data points cover at least half the page for an accurate gradient calculation. And finally, ensure equipment safety. Something like adding a counterweight to the clamp stand so the whole thing doesn't just topple over under a heavy moment. To bring this all together into one cohesive strategy, always fall back on the golden rule. Concept, pointing to the evidence, backed by reasoning, secures the mark. Whether you are analyzing a stretching spring or a balancing beam, this structured approach is, hands down, the most reliable way to bulletproof your practical data answers against a tricky mark scheme. But here is the ultimate test, right? What happens when the exam clock is ticking, you are staring at a massive data table, and you literally only have 3 minutes left to write out this perfect framework? Knowing the 4 steps is one thing, but executing them under severe, heart-pounding time pressure, that is an entirely different game. Data won't analyze itself, and a single decimal point can ruin your grade. You must master the time-to-answer writing system to survive those final high-pressure minutes. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click the explainer on your screen right now to lock down your timing strategy, and I'll see you there.